Good morning, everyone. Welcome back. It's last year we started a journey. The name for this series was inspired by a hero of mine, Carl Sagan, with his Cosmos series, which was, I believe, a wanderer's journey through the cosmos, something like that. And our personal voyage, I think, is what it was. And this is my localized and personal attempt to do something similar. This is a wanderer's voyage through a wonderful universe. And it's called the Quest series. Last year we started with the Bang, the Big Bang specifically. There are a few questions that are still largely unresolved when it comes to scientific investigation. One of them was, or remains, what made the Big Bang happen? And then what was the Big Bang? We have a lot of ideas about what happened after the Big Bang began banging, as it were, and I talked about that last year. And then we wrapped up last year with talk about cosmology, and in the meantime we talked about quantum mechanics and particle physics and relativity and things along those lines. This year, doing something a little different, we're bringing the focus more on Earth and terrestrial concerns. And what better to start, since we started last year with ideas about the Big Bang, we'll start with another big idea, and that is the origin of life. In science, it's called abiogenesis. It's theories about how chemistry and geology turned into living systems. And as you might expect, it's a relatively complex topic. In fact, as I was researching this over the summer, I knew what I wanted to talk about. Let me just turn my volume down on my phone so that I don't get interrupted. As I was researching this, I discovered that I believe I'm fairly competent with ideas around physics and mathematics and astronomy and a lot of the physical sciences. I even have some competency with geology and a few other things along those lines. But when it comes to biochemistry, I am humbled by the kinds of complexity and the kinds of astuteness that people who study and practice biochemical research must have a facility with. It's amazingly complex, and microbiology is complex, all of biology is complex, but it is an astonishingly complex field, and I'll do my best to summarize some of the highlights that entail origins of life. If you want to connect with our group, I'm a board member of the Humanists of West Suburban Chicagoland. We have several of our board members here with us this morning. We believe in an ethical philosophy, naturalistic explanation for the way the world works, and a scientific worldview. And we welcome you to join us. We have a series of programs that you might be interested in, aside from Science Sunday. These are some of the ways to connect with us. We're on meetup.com, where many of our activities, sometimes they're even relatively spontaneous. We do movie outings, sometimes we'll play board games. This summer we had a Pluto party. So keep an eye on meetup.com. We have a website too, it's not up here. It's hwsc.us. I looked at it this morning and it seems like it's got some problems with the rendering of the website. We'll try to fix that soon. And then the other way is we have a YouTube channel. We don't yet have our name associated with the YouTube channel, so you can't go youtube.com/HWSC, but you can search for us and you'll find last year's science lectures as well as many of our humanist programs up, and one from this year, a couple from this year. All right, let's get started. Abiogenesis, geology plus chemistry equals life. Well, we're going to talk a little bit about what is life. Hopefully we can answer that in a minute or two. We're going to talk about how chemistry and geology interact to bring about this thing potentially known as life. We're going to cover some ideas. Some of you may have heard of the primordial soup. I believe Carl Sagan dealt with that in one of his episodes of Cosmos. and the famous Miller-Urey experiment that made organic molecules from nothing but primitive gases and electricity. So we're going to talk about primordial soup, we're going to talk about muck puddles, we're going to talk about geothermal hot ocean vents and cold ocean vents. We're going to talk about something called serpentinization. We're going to talk about panspermia. And then we're going to wrap up today with some talk about eukaryotes. So I'll explain, if I used some words there that some of you weren't familiar with, it is my intention to explain those as we go along. If you have a question about vocabulary or a quick question about terms or definitions, etc., don't hesitate to just shout out at me or raise your hand. This is not particularly formal, so I welcome questions. And then we'll have some questions at the end. All right, so this is a recent view of what's called the wheel of life, with this idea that you get different kinds of major kingdom and species and phyla, some of those things you've learned about taxonomy in your educational history. This is a way of depicting that as a giant wheel. And you'll notice that a lot of the branches for that wheel seem to originate in the center. And that's where we're going to focus our attention today. Next month, I'll be giving a talk about natural selection and evolution, and maybe we can talk about all the rest of it, well, overview kind of way. So one of the questions that often comes up when dealing with life and questions about what is life, where did it start, you know, I don't want to step too far into the social debates that are, or the cultural wars that are going on, but one of the questions here is, when does life begin, especially in the context of a new organism being brought into this world? And the question is, does life begin at conception? Does life begin at birth? Does life begin at some intermediate point? Well, it's a badly framed question. Life on our planet has all evolved over billions of years from a common ancestor, and that life began about 3.8 billion years ago. And it's been a continuous chain of living beings ever since. So, if I had to make a statement, and I'll just make a brief one about the cultural war issue, I think it's a much more reasonable thing to say, when does personhood begin, if you're talking about human beings, rather than when does life begin. I think that's a problem that we often run into with any kind of cultural or scientific issue, is defining our terms and using the correct terms. Too easily, we can sort of unconsciously buy into the vocabulary that people use to describe things, when oftentimes that vocabulary is carrying along with it a lot of misleading connotations. That's my sermon about cultural issues for the day. So we want to focus on this center point. Sometimes it's called a tree of life. This happens to be a circle of life. And you'll notice that everything, every living being, every paramecium and pachyderm that has ever walked the earth and is alive today is believed to have originated from that central point in this wheel or tree of life, all those billions of years ago. That's the point we're going to zoom in on today. And you'll notice that near the center, there's a couple of branches that begin to happen. I mentioned eukaryotes. Let me talk a little bit about what a eukaryote versus a prokaryote are. Eukaryotes have that comes from a word that means true nucleus. So eukaryotic cells are cells that have nucleus. Nearly every living thing that you notice, and certainly every living thing that you can see with the naked eye, with a couple of extremely rare examples, are eukaryotes. They're cells that have nuclei. And eukaryotes bond together to make complex organisms. So most of the life on Earth that you think about, likely, when you think about life, is of the eukaryotic variety. There's another variety called prokaryotes, and those are things that are generally split into bacteria and archaea, two somewhat related mechanisms for living that are on the microscopic scale. And the leap from being an archaea or a bacteria to being a eukaryote is one of the great mysteries in the history of life. And we're going to talk a little bit about that today. But one of the things that I'll posit to you is that this picture, although much of the diagram is accurate, this particular picture is just wrong. Now, this isn't just me saying this. This is biochemists and people who research the origin of life around the world. Why is it wrong? Because if you look at it more carefully, and you do the DNA sequencing analysis to show how organisms are related to one another back through history, what you end up with is something that looks a lot more like this at the origin of life, which is a tangled bramble bush. In fact, it's so tangled that it's not discrete branches, but it's more like some kind of amorphous blob where the different strands intersect with each other, literally intersect and intertwine with each other at different points. There's this idea called lateral gene transfer, the notion that at its most basic level, the most primitive forms of life can literally exchange their genetic and biochemical information without any kind of reproductive process for the organism as a whole. That kind of transfer of information and chemical processes is believed to have been highly relevant in the origin of life. So that initial picture that showed a nice, clean little line going back to the beginning of life on Earth is clearly not the way that it happened. Here's a view of life, a history of life, the line there on the right-hand side. And I take a stab at making a definition for life. This largely is similar to the definition that NASA uses officially. Life are those discrete systems engaging in metabolic processes that do undergo Darwinian evolution. So we talk about discrete systems. That's the notion that you need to be enclosed in a boundary, where the inside is different than the outside, and from other discrete entities. This notion of boundaries is important, and I like studying and thinking about science from all manner of disciplines and all kinds of directions. And one of the things that I've discovered in the past couple of decades as I've studied different fields of science is that boundaries are incredibly important to almost any kind of science. Even political science, we worry about the boundaries. What makes a Syrian and what makes a Turkish person? What makes a Kurd versus what makes an Iraqi? What makes a Canadian versus what makes a Mexican? We worry about boundaries in the political sphere. We even worry about abstractions of boundaries. What makes a Democrat versus a Republican? Some boundaries are fairly easy to distinguish, like the boundaries of nation states or the boundaries between genders. But even then, we start getting into some fuzzy areas, right? What is male? What is female? The more closely you look at any given boundary, the more permeable it can become and the more slippery the definition can be. But for our purposes, we recognize that life in every known form is bounded by some kind of boundary. And in the cases of eukaryotes and prokaryotes, it happens to be a membrane composed of essentially lipid molecules that form a barrier against water. And those membranes are ubiquitous throughout the living kingdom. Boundaries become a very interesting phenomenon, and it's a phenomenon that is necessary for life. Metabolic processes. So that's one of the parts of the definition. Energy and matter cross a boundary, while waste heat and waste matter is expelled. The boundary defines in space and time a limiting point where metabolism occurs versus where it doesn't occur. And then Darwinian evolution, possessed of a means of reproducing almost identical copies of the system. You're not exactly like either of your parents, unless you're a clone. Even then, you're not going to be exactly the same. You've got two sets of DNA in each cell. You've got mitochondrial DNA and you've got your nuclear DNA, and even clones don't share mitochondrial DNA. Identical twins do. Anyway, this notion, if we start tearing it apart with our knowledge of the natural world, it also becomes slippery. We begin to see that there are exceptions. Mules don't reproduce. They don't undergo Darwinian evolution. They are discrete systems. They do have metabolism. Viruses don't have any kind of metabolism. They do have a boundary. They do undergo evolution. Regarding natural selection and evolution, human beings have developed to the point where we can intercede in what might otherwise occur in terms of natural selection. And it's a great thing. We want people like Stephen Hawking, people who have some physical disabilities. We want people like that to survive and thrive. We nurture people in our societies. We try to overcome with social and medical technologies some of the limitations that individuals face so that all people can live a happy, prosperous life. So in that sense, human society is striving to overcome the nature red and tooth and claw that comprises Darwinian evolution. And it's a good thing. As Richard Dawkins has said in some of his books, you wouldn't want to live in a society governed by Darwinian natural selection. And it's a good thing we don't. There's another potential kind of life on the horizon, computer life, synthetic life. We don't really have examples of this yet, but we can all pretty much imagine that it is plausible at some point in our future. So each of these examples is a counterexample to my trite definition of what is life. But even so, I propose to you that definition that we are discrete systems engaging in metabolism that do undergo Darwinian evolution is a perfectly workable definition for what we're going to talk about today and for the history of life on Earth. I want to talk a little bit about thermodynamics. I'm going to skip a couple of the thermodynamic laws because they're boring. But we're going to talk about the second law of thermodynamics. The second law of thermodynamics is one of the bedrock facts of life. In fact, when you, here I go with the culture war thing again. If you engage occasionally in some of the culture wars that would say that life is impossible, one of the arguments you occasionally come across is life is impossible because of the second law of thermodynamics. The idea of the second law is that if you put energy into a system, the energy that you imbue that system with will tend to spread evenly among all the parts of that system given time. So that you don't have what would be called an energy gradient. Now, I don't want to get too technical, but an energy gradient is what is necessary for most of the processes that we consider interesting. Moving a steam engine, walking, thinking, running a computer, turning on a light bulb, heating a home. All of these phenomena that we take advantage of whenever we think about the way energy is used in our environment takes advantage of an energy gradient. The second law of thermodynamics says that in a closed system, every piece of that system will devolve or evolve into the same energy state. So there are no energy gradients. There's no ability to tap into an energy source to do any work. The reason that's such a poor argument to countervail the notion that life could have arisen spontaneously is because energy gradients occur in open systems all the time. Remember, I was careful to talk about a closed system. We don't live in a closed system. Earth is not walled off from the rest of the universe. And specifically, we're not walled off from the sun. Secondly, we're not walled off from an energy standpoint from the hot radioactively driven core of the Earth, which is also a source of energy, and an energy gradient, an energy differential. The idea of the second law is that things always seek their lowest energy state, and if there's a certain amount of energy in a system, then that energy state will cause the energy to be spread out evenly. If you think of heat as just thermodynamic jiggling of molecules or atoms in a box of gas, eventually all those atoms are going to be jiggling at the same rate. The energy spreads out. Even if you inject some heat into a local clump of atoms, that energy dissipates. So the argument against using the second law, or against the idea that energy can spontaneously form complex systems, imagines that we live in a world kind of like this diagram, where in order to do anything complex, we have to go all the way from the bottom, all the way back up to the top of the energy gradient scale to be able to extract useful organizing energy from the system. But in reality, it looks more like this. You can still be running downhill all the way, but you can have local peaks and valleys. You can have local energy gradients, even though the overall trend is towards equilibrium and dissipation of that energy. Here's an example in nature of that kind of self-organizing energy gradient principle. This is a hurricane or a typhoon, depending on which hemisphere you live in. And the energy gradient of temperature between the atmosphere and the oceans, or between different parts of the atmosphere, different parts of the ocean, that energy gradient, which happens at certain times of the year, can drive a complex energetic process that is clearly organized. I mean, a hurricane is not just some random assemblage of thunderstorms. It has a very definite, reproducible structure. So this is proof positive that even aside from the notion of the origin of life, you can have a complex, it's called a complex dissipative system that arises spontaneously from energy gradients available in a system. Here's another interesting phenomena. These are mud cracks. Well, these are patterns. These are patterns that arrived naturally because of physical and geochemical and geothermal processes. There's nothing magic about this. There's no vital force. There's no supernatural entity that comes down and carves these into mud. Nature, when provided with constraining boundaries combined with an energy gradient, will often form patterned systems. And that can even happen on a molecular level. We're going to talk about that. But this is one of my most favorite examples of natural patterning. These people are out here, I don't know, they spend days raking all of these rocks into these circles to fool us into thinking that this is natural. No, that's not right. These are hikers or scientists, I don't know which, but they come across this terrain that is created by natural processes. This is pattern earth. This is a general term, pattern earth. What happens is the freezing and thawing cycle naturally separates and differentiates the small stones from the larger stones, and it tends to create tiny forces that over many, many seasons cause the gravel and chert that is collected in these flat glacial northern regions to differentiate into these patterned circular features. It's amazing. Nature can make nearly perfect circles, given nothing more than rocks and energy. Here's another view of patterned Earth. Now, speaking of complexity, it is one of the slipperiest notions in science. There is no equation like E equals mc squared that talks about what is complexity. How do you measure it? How do you know it when you see it? Well, maybe that's the only way we have for defining complexity, is that we know it when we see it. It is one of the areas of scientific study that is most fertile and open for exploration and innovation. We need a grand theory of complexity, because right now it's mostly semantics. I would posit that most science starts with semantics. We talk about energy, and I assume that people talked about energy, or in some language they used a term analogous to energy, well before we knew that the units of energy were kilograms per meter squared per second squared. Right? So science is this progression. You can see that stars have different colors well before you get to the point of understanding what physical processes drives different stars to have different colors. So science begins with semantics. And one of the areas where science has not moved very far beyond semantics is this notion of complexity. And that's one of the things I think that's hampering some of our progress in social sciences and economic sciences and origin of life sciences and in many other sciences, is to be able to quantify and deal with complexity as its own set of attributes within interesting and complex systems. So I can't even talk about it without referring to it. How do we look at complex systems? By recognizing complexity. Easy. Here's some complexity that arises because of a very simple mathematical formula. This is called a fractal, or this is one version of a fractal. All right, so let's talk a little bit about biochemistry. One of the reasons that life can exist on our planet, and potentially on others, is because nature has built into the chemical energy relationship of many molecules a hump. You see this hump that starts here, and then this giant hump, and then there's a lower energy state. This is essentially the amount of energy. You see that going from this state to going to this state would entail being in a lower energy configuration. And remember what I said about thermodynamics, things like to be in a lower energy configuration. Oh, I use the term like, I hate that. Natural systems tend to behave in ways that minimize the energy. I don't like anthropomorphizing it with terms like. So, bad on me. In any case, natural systems tend to act in a way that minimizes their energy. So you'd think that this system wants to... You'd think that this system is driven by some natural process to enter this energy state. Well, it is, but there's this giant energy hump in the way. They have to get close enough together in order to react with one another, for example. There's this notion in chemistry called a catalyst. And one of the things that a catalyst does is it significantly lowers the size of this hump, such that in a world where suddenly you're in a world where water is a liquid, the amount of energy available from water molecules jostling about can then be sufficient to potentially drive this action to happen. If we lived on an Arctic planet like Pluto, then the amount of lowering required to get some of these processes to happen would be tremendous compared to what happens on Earth, where we live at about 30 degrees centigrade, something like that, 70 degrees Fahrenheit. We are very fortuitous that water molecules can provide enough of a bump to drive many interesting reactions if they're mediated by catalysts. So that's called that hump is called the activation energy, and you can lower the activation energy by providing a catalyst. Life is a process of coaxing chemical reactions over the activation barrier, then capturing the free or freed up energy to drive even more activations. Life is all about using energy to locally maximize entropy through catalytic action. Life, in that sense, is the universe's best catalyst. A self-perpetuating, invasive catalyst far better than pure mineral catalysts. We're going to talk more about catalytic reactions and how that relates to life's chemistry in just a minute. But I want to talk about some of the molecules of life. Back in 1953, Stanley Miller and Harold Urey did a famous experiment. Miller was actually a graduate student. Urey had already won his Nobel Prize. And Stanley Miller came to his thesis advisor, Harold Urey, and said, I want to try to make living molecules, the molecules of life. And Mr. Urey said, that's really a dumb idea. I don't think it's possible. I think you're wasting your time and you're never going to finish your thesis. So I'll tell you what, I'll give you 6 months and some lab equipment, and of course you're not going to succeed. And then at the end of 6 months you're going to come back to me and you're going to say, could I have a real thesis topic, please? So in a couple of weeks, Stanley Miller set up this experiment that he had in mind, and he turned on the spark, and it worked. So this idea that he had was to combine molecules that one might find at the time. They thought these kinds of molecules like methane and hydrogen sulfide and sulfur dioxide, carbon dioxide, molecular nitrogen, water, that the early primitive Earth was bathed in these primitive molecules. They certainly aren't accepting that the notion of organic chemistry just means anything with carbon. These aren't the molecules that life inherently uses in most cases. What he did was he ran a spark through an enclosed vessel that had these kinds of gases, water vapor, nitrogen, etc. And after a few days, this brownish red gunk accumulated on the surface of the glass, and when they looked at it, they found amino acids. They found the building blocks of proteins. And since 1953, here he is, and here's his experiment. This is Stanley Miller. He passed away, I think, about 5 years ago or so. But just a beaker with gases through which he ran an electric spark. And this notion that all it takes is a vital spark to create life is deeply embedded in our cultural consciousness. We think about the vital force. We used to have a scientific idea that was taught in schools called vitalism, that you take a piece of gunk and you imbue it with the vital force. And it becomes alive. And this notion of vital force took a long time to work its way out of our scientific, oh my goodness, there's even this. Alive! It's alive! Right? So this notion of vital force is now no longer believed to be relevant. There is nothing magical, nothing special outside of biochemistry. If you look at the metabolism of cells at the deepest level possible, you can even look at it from a quantum mechanical standpoint and see that quantum mechanics plays a role in some of the organic catalysts that facilitate the actions of life. But in all of those, there's no room for magic. There's no room for the vital force. It's just chemistry. It's just chemistry and electrons moving around and water molecules being bumped around by thermodynamic tendencies and reactions. In fact, when you get to the scale of the atomic, it turns out that there's something really special about that scale from a natural physics-y standpoint, and that is that the energy of a molecule at room temperature, or give or take a couple hundred degrees, and the energy of electrons being bound to an atom, and the energy available if you collect some electrons or protons and move them across a boundary. These electrical potential, the ionization potential, the thermal the thermodynamic energy of a system at nearly room temperature, all of those kinds of energies can be easily interchanged. Now, at our scale, we have to go through a lot of complex gyrations to get energy converted from one form to another. We convert the potential energy of water in a lake to electrical energy, and it takes a complex machine to do that, and it's highly inefficient. You certainly don't take all of the energy associated with the potential of that elevated water and turn all of that at near 100% efficiency into electrical energy. But at the scale of life, these different energetic processes have nearly identical activation energies and outcome energies. And furthermore, when we talk about the molecules relevant to life, we look out in the cosmos, we have found that the cosmos is littered with the molecules of life. Now, these aren't living things, but they're the same kinds of amino acids and lipids and gases that are entailed in the metabolic and structural processes of life on Earth. And they're all over the place. One of the things, I give a talk on Drake's equation, and one of the things I talk about is this notion that, well, maybe there's silicon-based life, or maybe there's aluminum-based life, or something like that. It's unnecessary. Carbon is everywhere in the universe. And carbon is such a gregarious and wonderful molecule that there's no reason to posit that natural processes would have to go through some kind of complex processes to exclude carbon from any kind of metabolic chemical reactions. Carbon is gregarious. It's there. It's like, hey, use me. I'm a great atom. Everybody loves me. I can make diamonds. So there's carbon-based molecules everywhere. We can look at the dust around baby stars and find the molecules of life. We took samples out of a comet in our solar system and found organic molecules. They're everywhere. And that's one of the ideas that led to this notion that maybe there was this cosmic organic muck on the Earth several billion years ago before life existed. That biomolecules, the precursors to life, were just as abundant in Earth as they are in meteorites and comets and space dust today. And that's probably true. So, what's special about Earth? Well, I've said it several times, the notion that we have a temperature that allows for liquid water. The fact that we have a molten core. There's another energy source available to living things other than the sun. The Earth has a magnetic field that shields us from a lot of potentially dangerous solar radiation particles. And there's this little thing that happened about 4 billion years ago. There was a planetoid, it was called Theia. We had to put a name to it, so we call it Theia. About the size of Mars. Our solar system was young. It was still a bit misbehaved, if you will. And this Mars-sized planet just kind of bumped into the Earth. And when that happened, well, it was fairly catastrophic, as you might imagine. So what they think happened was that the energy released in the collision essentially made all of Earth molten and all of Theia molten. And since it was essentially liquid at that point, you know, when you throw a pebble into a pond, it gets this little blob that splashes up again. Well, that little blob that splashed up as a result of the collision was just largely the less dense crustal material, the same kind of stuff that makes the crust that floats on the continental cratons in geologic terms. And if you look at the way our moon is currently constructed geologically in terms of its density and whatnot, it's made of the same kinds of stuff that Earth's crust is. It has very little iron, very little of the heavier geologic minerals compared to Earth. And what that did was it probably took a lot of crustal material away from baby Earth And that was a good thing, because it led to the availability of something called plate tectonics and fault zones that could pump the heat of the Earth's core up to or near the surface. So this idea of plate tectonics and thin crust might be a direct result of this chance collision with the thing that made the moon. Here's an artist's representation of that. It was a very violent thing. It's also thought to be responsible for the fact that the Earth's axis is tilted by about that much. And that's why seasons exist, is because of being thrown a kilter. All right, so which came first? The chicken or the egg? Now, I posit, of course, I like thinking about all kinds of questions. I have sort of a philosophical bent. And I think that if you believe that the world was created magically by some entity, necessarily you must conclude that the chicken came first. However, if you are persuaded by the evidence of science that natural selection is necessarily the best explanation for the reason that life exists on our planet and all the various and wonderful species, then something slightly different than a chicken laid an egg that became a chicken over many generations. So maybe the egg came first. But in this context, you can combine them and have kind of a chicken-egg soup. The reason this is relevant for my talk, other than funny pictures, is that there's this question among origin of life theorists about which came first: structure or metabolism, or information replication. And different groups have posited different answers to that question. Structure. This is a representation of a typical eukaryotic cell. Remember, that's a cell with a nucleus. It's got all kinds of complicated little gizmos in it. It's got Golgi bodies and cytoplasm, and it's got endoplasmic reticulum. I love saying that word. And it's a very complex system in its own right, and very structured. So did this structure arise early in the generation of life from non-living systems? Or was it metabolism? When I was researching this topic, I came across all kinds of different representations of the metabolism pathways available to and exploited by life. And it's a poster that could be normal-sized print that could fill up that wall. I mean, it's just amazing, the complexity. I can't begin to internally digest all of that information. But here's a little piece of what happens in cellular metabolism. Crazy complex stuff. One of the keys is this electron, or this acetyl cycle over here. And then this is pretty interesting too. This is a very basic metabolic process in every single living thing, whether it's a eukaryote or prokaryote. And it involves, you see these things right here? Those are H pluses. Those are hydrogen ions, otherwise called protons. And that's in the ATP cycle. We're going to talk a lot about that in a minute. Or was it information processing that came first? You know, you probably recall, if at least dimly, the idea that DNA becomes RNA, which becomes proteins, which become flowers, orchids or something. So that's the information processes that are in a cell. Well, current thinking is that the likely answer is that metabolism came first. Because remember, in order to have structural complexity of any form, regardless of what complexity means, you need to have an energy gradient, and you need to be able to use that energy gradient to form complex systems. And if this happened aside from the action of what we call life, then it must have been a purely natural process. There must have been a natural energy gradient available at a microorganism or micro scale, available to be exploited to drive the formation of structure. So metabolism seems like a reasonable first choice. And in fact, talking about those hydrogen ions or protons, every living thing, with a couple of exceptions that are well explained, have mitochondria in them. And mitochondria are the batteries of cells. And even bacteria and archaea use something very similar to the way that mitochondria process protons to make energy available. They build up this proton gradient across a membrane. That's the little tiny blue circle railroad track looking thing. That's the membrane. And embedded in those are some chemical machines, literally machines, with cogs and wheels that grab onto water molecules or other molecules and strip protons off of them and then transport those protons across the gradient so that you have a charge, just like in a battery. Just like the two poles of a battery separated by a non-conductor. You've got charges across a membrane. And that simple chemical process is the same kind of battery that literally is at the foundation of every metabolic process on the planet. And by the way, photosynthesis evolved after this. So the notion that the first living things on the planet ate sunlight and used it to split water molecules, which is what photosynthesis is all about, that's not true. Photosynthesis was a latecomer to the show. So where on Earth could the energy gradients have come from? Well, we'll talk about that in just a minute. We're getting to the good part now. See, I'm already on nearly an hour in. Key discoveries. All right, this is the text portion of the talk. I put a nice cute kitten on there so that you would be distracted from the ugly text. Photosynthesis is not the oldest metabolic pathway. It uses energy from electrons kicked around by sunlight to move protons. There we go again. It's moving protons. Photosynthesis, even though sunlight kicks electrons off of atoms and molecules, it uses all of that energy to move protons. You see a common theme here? Proton gradients and their movement across boundaries through literally molecular turbines drives cellular energy. To find the first metabolic geophysical process, we need to find a place with a natural proton gradient. Mud puddles, clays, tidal pools, they don't have it. This is a picture of a formation deep under the ocean. This is actually, I don't recall if this is something called a white smoker or black smoker. The idea is that there are chemicals that are heated by Earth's core that bubble up through cracks in the Earth. I think it's probably an error in the way I constructed this slide. So this is actually something called White City. And it's somewhere in the Atlantic Ocean. And it's a fairly modest temperature phenomenon where warm, mineral-rich water loaded with minerals bubbles up through a mineral called olivite, olive green. This is some olivite. This is the show and tell of the talk. I don't have anything particularly exciting. You're welcome to look at this after the lecture. This is a piece of basalt, very dense and heavy, and there's some olivine crystals on it. And it turns out that if you bubble some gases that are common in Earth's interior, like hydrogen sulfide and methane, some other gases, if you bubble those up through olivine, it causes a chemical reaction that gives rise to something called serpentine. Beautiful, beautiful rock. And that chemical reaction is you've heard of acids and bases? It's a basic reaction. It creates a base pH environment. And the seawater on primitive Earth is believed, with some good evidence, to have been slightly acidic. So if you get an acid in seawater, and this geochemical process of this bubbling gradient that is somewhat basic, then the transformation of olivine into serpentine can produce calcite and carbonate structures that form these giant white pillars. And this geothermal system can persist for tens of thousands or perhaps 100,000 or more years. So it's a very stable geochemical environment. And furthermore, if you take an acidic ocean and a basic gas expulsion from these geothermal vents, you get a very high difference in pH. And when you have a high difference in pH, catalysts that occur naturally can react and drive chemical reactions a lot more efficiently. This is another picture of the Lost City Formation. There's a video available, freedom to BBC, PBS. One of the big producers of natural scientific videos has some Life in the Depths, something like that. It's a video that you can get about the ecosystem associated with this modern vent environment on the ocean floor. And it's located there in the Pacific Ocean. Atlantic, sorry. And it gives rise, let me go back. It gives rise to proton gradient naturally. Also, in the process of serpentinization and the release of that calcite that forms those white structures are littered with microporous holes. Tiny little holes about the same size as bacteria and archaean. So there's a natural environment that has ready-made tiny little compartments, and around these compartments and within these compartments, a proton gradient builds up. And that can help drive autocatalytic mineral processes that use largely iron and sulfur, which were abundant in the early ocean before the great oxidation event of 1044. Now, it is much earlier than that. So there was all this dissolved iron in the water, and there was sulfur coming out of the vents, and there was this proton gradient. And here's the amazing thing. If you look at life's key enzymes that drive that ATP cycle today, you know, those hydrogen ions, the enzyme that facilitates that reaction is a bunch of carbons and hydrogens and all that other normal stuff. But they encage sulfur and iron atoms. And it's the sulfur and the iron that cause the reactions to happen. They're the active site in that enzyme. You're not used to thinking, I wasn't used to thinking about iron and sulfur being organic molecules. But the key metabolic processes of all life uses fool's gold embedded in the enzymes. This happens to be from Morocco. It's a fossil. There's a region in Morocco where fossilization has happened because iron sulfides have permeated through the rock, and it forms fool's gold fossils. So these are my three rocks to explain this process. And inside these tiny little cells, these naturally occurring geochemical cells in this structure, you can imagine that some of those molecules that are necessary for life, like amino acids, were naturally accumulated, just like they're everywhere on Earth. And if you wait long enough, maybe a few million or hundreds of millions of years, it seems plausible that some of those molecules of RNA, these little RNA micro-worlds, if you will, the amino acid micro-worlds, might link together to form tiny little biomolecules that have the ability to to self-replicate. And remember, nature tends to drive systems to a lower and lower energy state, and the faster and more efficiently that can happen, the more preferred it is in natural processes. So anything, any chance assembly of amino acids linked together into an RNA chain, and by the way, there's a scientist that gave a talk at Fermilab recently, Sozak, I can't recall his first name. Anyway, he gave a talk about how RNA has a typical structure in today's world, but they have synthesized a sloppy version of RNA that is more consistent with just random joining together of base pairs. And they found out that this sloppy joining together can also act as a biocatalyst, much less efficiently than normal, modern RNA, but it works. And it's a little better than nothing. And once we have a little better than nothing in a molecule that self-replicates, we're off to the races. So 3 steps to simple life. Step 1, proton gradients across inorganic substrates in the cell walls of naturally occurring formations drove the formation of small organic molecules, which improved the natural, otherwise pre-existing catalytic capacity to drive things towards a lower energy and thermal state. There is no words that I'm just reading because I didn't want to work. It's just my 3 hands. Hand number 2, simple dissipative structures involving biochemical metabolic pathways increased the entropy production. They became self-organizing dissipative structures. This is plausibly when lipid cell membranes were organized. It turns out if you take the molecules associated with lipid or fatty, what we call fat, those are really readily available in nature from inorganic processes. And if you drop them in water, they form little sphericals. Little soap bubbles, if you will. Step 3, this is my 3rd hand. The plentiful reactive precursors, the sheltered environment, the natural proton gradient, and the emergent biochemistry was driven by thermodynamic processes to use ever more complex biochemistry to hasten attaining thermodynamic equilibrium. This energetic reward for greater and greater efficiency incentivized the construction of simple RNA-like enzymes, which then began to encode and transform and transfer information about biochemical structure. And we're off to the races, as I said. So there are still some issues that are yet to be solved. There's this notion of chirality. Chemistry doesn't seem to care whether you've got a molecule, organic molecule, that is built facing one way or the other. And maybe it was just lucky chance. Maybe the opposite-handed molecules were in some primitive life or prebiotic life or replicating molecules that just got out-competed. Maybe that's why we only see molecules of a particular orientation in all living things today. There are, however, chirality differences in archaea and bacteria. So there's some indication that the 2 bedrock kinds of living organisms might have evolved along different pathways for quite some time, at least when it came to building their membranes. Moving out of those rock cells and moving into membrane self-contained cells. They used slightly different chemistry to do that. In 2000 and since, Robert Hazen and other researchers have found that there are certain chiral minerals on Earth that preferentially catalyze molecular interactions of a particular associated chirality. Jack Szostak, that's the name of the fellow I was trying to think of. He won the Nobel Prize in Chemistry in 2009. He's found that functional RNA that is chemically messy and it can still work. In fact, he took some literally randomly created millions and millions of different kinds of tiny little snippets of RNA, and he put a chemical into his device. Let's call it a beaker, for lack of a better term. And he poured out all of the RNA molecules, and the ones that interacted with the little chemical that he put into his beaker stayed. and then he used those to serve as templates for a new generation of RNA molecules. And so he selected over time by just washing them away and replenishing the raw materials for RNA construction. He formed RNA that very inefficiently but plausibly replicated itself and preferentially bound itself to a particular mineral. It's plausible that nature did something similar. RNA assembly doesn't seem to like water. That's one of the problems. Maybe RNA self-assembling replicators evolved separately in a drier environment, or maybe some gaseous process or some physical process unhydrated or drove the water out of some of these little tiny cells in that environment I talked about. Perhaps both proton and aqueous gradients and RNA synthesis all happened in the same general area within something analogous to that white city. So remember this thing here. Here's another interesting view of it. So this kind of zooms in on the middle. You see archaea, bacteria, and eukaryotes. This is the second half of the talk, which should take about 15 minutes. And in this view, we're going to zoom in on this interesting spot. You see, everybody who draws these diagrams just leaves this alone and just draws it like, oh, it happens, right? This is where they branched off. Why? Why did they branch off? What was the branching of it? There's this notion of Luca versus Lika. Luca, last universal common ancestor, the thing from which all other life is derived. There may have been other living things at the time, but their ancestors, or their progenitor, their descendants, have all died out or been eaten. So Luca was the last universal common ancestor, and then there's this idea of Lika, which is last eukaryotic common ancestor. And remember, we're eukaryotic creatures, as are everything we can see with our eyes. And this idea that going from bacteria and archaea to eukaryotic life was a transformative event in the history of life of our planet. If you can imagine that life arose relatively easily on our planet, life comprising things like bacteria and archaea, then it's much harder to imagine how eukaryotes arose from that. But somehow, between 3,500 million years ago and 2,000 million years ago, it happened. And we're going to talk about what possibly happened there. So here's last universal common ancestor candidate, something like a bacteria or an archaea. This is representative of each kind. Lynn Margulis came along in the 1960s, and she said, you know what? I bet that an archaea ate a bacteria. And everyone said, oh, that's stupid, right? It would just be dissolved, it's food. Well, what if one got eaten and didn't dissolve? What if it got consumed by an archaea and maintained some integrity and kept living inside the other organism? If we look at our cell walls, the cell walls of every eukaryote, it looks a lot like the cell walls of an archaea. Bacteria have a very different cell wall, and oh, by the way, they look a lot like the cell walls of mitochondria that are in every living cell. Remember those little proton batteries that we carry around? So this idea has a lot of plausibility, and oh, by the way, there's two separate sets of DNA. If you look at our cells, the eukaryotic cells, the mitochondria have their own DNA, and the rest of the cell has its own DNA. Remember when I talked about lateral gene transfer? If you've got two organisms living in close proximity, they can be very gregarious about sharing their DNA pieces. That has happened over time. If you look at eukaryotic DNA sequences, you see that pieces of what might otherwise have been the DNA for the bacterial piece that became mitochondria now live inside the nucleus. And the mitochondria has retained those parts of its DNA code that facilitate and only facilitate this energy generation. It has become specialized, and it offloads many of its other metabolic processes to the nucleus. Did you get all that? I told you this is mind-blowingly complex.
Is there a test after this?
No.
What you're saying is the mitochondria keep living inside the cell structure, give up certain functions that they don't need anymore, and maybe the nucleus takes care of the cell regulation, but the mitochondria takes care of its new determined functions.
And that function is specifically the energy generation capability of the cell. And not only that, I don't have time to go into details of this, but I've got 20 minutes left, so one of the things, there's this book called The Vital Question by Nick Lane, mind-blowing. It is one of the densest, richest science books I've ever read, and it was just published this spring. Nick Lane, I'll have more about it later. He talks all about this eukaryotic emergence from early life. And one of the things that he says in his book is that if you take the metabolic process of a bacteria or an archaea and you try to scale it up in size, it fails. Because the metabolism happens at the surface, at the boundary. Remember that proton gradient across boundaries? If you try to scale that up in size, it fails because the volume grows much larger than the surface area grows. So what happened with eukaryotic life is it took this tiny little efficient energy battery with its own self-contained boundary to maintain a proton gradient, and it incorporated it into the cell and uses that as an energy source, and now the eukaryote is energetically free to expand and become this complex thing. So that single synthesis between an archaea and a bacteria provided a superstructure on which all resultant life has evolved that isn't bacteria or archaea. And by the way, if you add up the mass of all the archaea and bacteria on the planet, and the mass of all trees and plants and elephants and moles and everything, the archaea and bacteria outweigh them by far still. But this is, for us, some of the most interesting life, and certainly far more complex. Had that synthesis, had that symbiosis not happened, simple life only would exist on our planet, and there would be no large bodies, no multicellular organisms, none. So it's very plausible that if life exists elsewhere in the cosmos, and we've seen the geothermal, geochemical processes which occur naturally here, and likely occur nearly anywhere that has molecules and atoms, these molecules and atoms on which the metabolic processes of life are predicated are ubiquitous in the cosmos. If you find another planet that has life, there's a good chance it's only going to have these tiny little pieces of life. That this eukaryotic synthesis, symbiosis event, was the really rare thing. So maybe there's 1,000,000 to 1 or 1,000,000,000 to 1 if you look at the planets that only have simple life and the planets that have complex life. Of course, we ended up on a planet with complex life. There's nothing divinely magical about that. It's just the laws of probability given 100 billion stars in our galaxy. Can life evolve twice? Well, probably not on the same planet, because biomolecules are yummy. Just like ice cream. Right? So all of these primitive processes that gave rise to autocatalytic organic molecules, those autocatalytic organic molecules would be tasty treats to bacteria and archaea. So they're not likely to stick around long enough to undergo natural selection processes and evolve again. Here's an analogy for you. This is a car that was invented by a Frenchman. Any guess when this happened? 1769. This is a steam-powered, self-driving machine. See, there's a seat, and there's the handles, and there's a little steam tank with a fire and whatnot. And this is a modern, high-efficiency car, Formula One car. It would be like living in a world where these kinds of mechanical devices were used commonly as opposed to something closer to that. Well, they're out-competed. It's not going to happen. Nobody wants to drive around in one of these. You can't get where you're going fast enough. Nobody wants to use these simple inorganic biocatalytic processes because they don't happen fast enough. Natural selection has evolved that process into a complex, beautiful system that is far faster and more efficient. And why not use it? There's one exception to this. In 2010, off the coast of Japan, near an undersea volcano about a mile deep, some researchers pulled up a fish, which wasn't remarkable, but on the fish, or in its gut, I forget which, there was this creature. This is the only picture that exists. This is the only sample that's ever been found in 2010. They sectioned it, they sliced it up and whatnot and took pictures of it. And so biochemists haven't had much of an ability to dig into it and see what the metabolic processes are. It's dead, and it's cut up. But look at this, it's got a nucleus, and it's got this sort of endoplasmic reticulum. In fact, if you look carefully, you see this wadded up thing, that's a whole separate cellular membrane, enclosed in this cellular membrane. So this is almost like a relatively recent descendant of a relatively recent, geologic era speaking, symbiosis between two primitive archaea or bacteria, or one and the other. Remember I was talking about that eukaryotic event that formed complex life? It looks like that may have happened at least once more. These are the books that I took a lot of the content from this from. I can tell you more about them at the end, during the time afterwards. I particularly recommend these two at the top, The Vital Question and Life's Ratchet. Not that these aren't excellent as well. This one talks about how cellular enzymatic processes, the metabolic processes of life, leverage quantum mechanics to move protons via superposition from one side of the molecule to another. This is just kind of an overview about life's origin and where it might be going. But these two are exceptional. And that's it. I'll take questions, and then we got 10 minutes left on my hour and a half. So go ahead.
You going to be posting this lecture on YouTube at all?
Yeah, it's going to go up on our YouTube channel that I referred to at the beginning.
Okay.
So it might take a couple weeks because I have to edit it and whatnot. Other questions?
After I heard that talk at Prairie Lab, and the description of how these various structures are formed, which begin to come under a number of what you might call life, there also must be depth. So there must be a mechanism by where these structures wear out.
Yes.
What is it?
So the question is, this is how life arose. Why death? Where did death come from? So this book, The Vital Question, actually devotes quite a bit of ink to that. And the short answer is that eukaryotes and bacteria are immortal for all intents and purposes. They don't have clocks that run down. Every eukaryotic life form known has a finite lifespan. And what he postulates in the book is that it's part of the trade-off between having a metabolic process separate from your information encoding process, having a mitochondria and a nucleus separate from one another, that the chemical and physical distinction between those is really relevant. That leads me to another point that is in the book that I thought was incredible. He predicts, just from thinking about it critically, that sexual reproduction happens because of mitochondria and nuclei being separate. And he predicts a second thing. He predicts that the gamete lines, the cells that make the eggs and the sperm, he predicts, certainly you call it a post-diction because we know this to be true, but he argues philosophically and scientifically why this is so plausible and why it's almost certain to have happened this way. that when a female is born, she's generally born with all the eggs that she will have in her lifetime. And when a male makes his reproductive cells, the sperm cells, those are made continuously throughout life. Well, it's the eggs that carry the mitochondria. And the mitochondria, remember I said they had a tiny little DNA, tiny little fragment of coding information? That's really fragile. It's not able to sustain many errors over the course of being reproduced to make a multicellular organism. So it makes perfect sense that egg cells are made when the organism is young and healthy before the many mutations have accumulated, because you don't want those mitochondria to change. They have the DNA that is necessary to metabolize for life, and you don't want it to change. And secondly, the sperm cells that carry the nuclear DNA, or parts of the nuclear DNA, who cares if that's changing? There's so much junk in that it doesn't matter. It's not as sensitive to change. So just by looking at the energy and chemical pathways entailed in the way that a eukaryotic cell is constructed, he predicts that there are two genders, and two sexual genders, and that their gamete cells have these very different characteristics. And he also talks a little bit about death and why death may be an inevitable consequence of some of the metabolic pathways. I really recommend the book. Yeah, Mike?
There's some aspect which I've been looking into a lot, that without death in the cellular structure, you don't get evolution, right?
Sure.
You have to have things that are dominant now become mutated and die and pass their mutated information on to more species, or else you don't get evolution.
So I agree with that, but I think it's putting the cart before the horse a little bit, philosophically, because as I will talk about next month when I cover natural selection and evolution, nature doesn't have a plan. There's no end goal that evolution is striving for. So to say that without that kind of cellular death, evolution wouldn't be possible, and it's a good thing that it is, well, that's a consequent. It's not a prerequisite, right? So just like bacteria and archaea are effectively immortal, there's nothing wrong from a metabolic and biochemical standpoint of having that kind of immortality built into the cellular structure. There's no a priori reason, there's no driving energetic force that makes evolution necessary. It just so happens that because of the metabolic pathways entailed and the fact that they do lead to cellular death and complex DNA in the nucleus, a eukaryotic cell's DNA is far more complex than any bacteria, and it's able to do that because it's got an energy surplus. And so all of this is entailed in this notion that complex life is mortal. And then radiation and other forms of mutation simply capitalize on that to cause natural selection to occur. So it's a very subtle argument and a distinction I would make. But essentially, you're right, without death, without a genome going extinct, how could you have new ones arise? Other questions? Yeah.
So where does viruses fit on the timeline? Are they needed? Are they always needed? Do they help the whole process of evolution, whatnot? Or are they just kind of an obstacle? Or?
Sure. So the question is about viruses. So as recently as a couple of days ago, I was talking to my partner, Dave, who likes biochemistry more than I do, about the potential role for prions and viruses, things that don't have any kind of metabolic capability in and of themselves. Are they life? I alluded to that when I was talking about exceptions to my simplistic definition of life. So the question is, are viruses necessary? At what point in the history of life did they evolve? I haven't read anything that tells me the answer to that yet. There may be answers that I haven't encountered, but it seems plausible to me, it's just me, that a lot of times we see effectively de-evolution. We see complex things that become simpler because they, like the mitochondria, can leverage the fact that it exists in a sheltered environment of a host cell. So it loses a lot of what would normally have originally been part of its complexity. Red blood cells don't have mitochondria. They're not necessary. Red blood cells just transport other molecules around. They don't metabolize. So there are exceptions to nearly every rule in biology, and it seems plausible to me that viruses arose from life and not before life, but I don't know that.
Bill Nye's book, his most recent book, actually talks a little bit about viruses.
Okay.
So if you are interested,
I am.
that would be a good book to...
Thank you.
Yeah.
Bill Nye's new book.
Bill Nye.
Bill Nye, the science guy.
Yeah, I can't remember the title of the book, but it just came out within a year or so.
He of the resplendent bow tie.
Yes.
Other questions? Yeah.
They just found a new super-sized virus in Siberia, which I think is going to go a long ways towards answering some of these questions because it's bigger than most bacteria.
Wow.
So this is going to be an interesting area of discovery. As we, through many, many centuries,
Right.
we have ignored viruses, but now that we're looking for them, we discover that viruses are outnumbering all of the eukaryotes.
Right.
And oh my,
Yeah.
what's missing here?
So I think there's a profound lesson of science in that. A lot of times stuff you sweep under the rug or say that's irrelevant, you know, like I was thinking about with viruses and prions, which are misfolded proteins. A lot of times when you look at things like junk DNA, you find a world of complexity and implication that no one ever suspected. And I'm going to talk about that not next time, but the lecture, what's September? In November is going to be about genetics and epigenetics and DNA and what junk DNA is or isn't. So yeah, look in the places that everybody says is meaningless and you'll likely find some light bulbs. Other questions? Yeah.
Back about the Stanley Miller experiment. So that's 1953,
Yeah.
and he proved by sending a spark through these gases and water, it did produce amino acids.
Yes.
Yeah. So have there been subsequent, experiments,
Yes.
research? Because you would think that we would be hearing if something like that. I mean, when I was growing up, I don't remember that even being a topic in biology.
So his experiment made the cover of Life magazine, and Watson and Crick's discovery of the double helix for DNA, which happened the same year, didn't. So at the time it occurred, the Miller-Urey experiment was considered astonishing, groundbreaking, newsworthy science. But since then, the number of chemical and physical processes that can lead to the generation, the creation, another word I don't like using because people bring their baggage to it. The geologic and physical processes that lead to the creation of organic molecules is common in the universe. Everything from ultraviolet light working on cosmic dust to electricity through simple gases to these hydrothermal vents that fractionalize different chemicals and create proton gradients. The number of processes that can give rise to organic molecules is so widespread that we've stopped hearing about each individual discovery.
Okay, yeah.
Yeah, Mike?
It's an interesting aspect that a lot of people don't realize, that life developed on Earth very quickly, relatively soon,
Right.
soon in the beginnings of Earth. Earth is registered somewhere around 4.5 billion years old, and life is generally said to have created at 4 billion years old. So in a relatively short amount of time, this thing that was a volcanic,
Maelstrom,
just a wild place, settled down to the point that life could form on it. It's an interesting, important topic to talk about. And the second is that life existed for almost all of the time that we know of it as the most complex form of life on Earth. For almost 3.5 billion years of that, 4 billion years was as a bacteria,
Right.
bacterial stage.
Yeah, so it could be that the generation of life from geologic, geochemical, and physical processes is, I use the term reservedly, easy. Right? If you have a planet's worth of laboratory and a huge amount of natural processes, it could be that it's highly plausible and likely that simple life will arise. But this eukaryotic symbiosis may have been far more rare And we may find eventually that it's not very common in the universe. All right, I think I've run against my time limit, so if you have additional questions, I'll hang around for a bit. We're going to go for lunch, several of us, just down the street at Tom and Eddie's Burger Place. And thank you again. I'll see you next month.